Ladies and gentlemen, I'm a first-year PhD student from the doctoral school at the University of Science and Technology in Bydgoszcz, Poland. A multiaxial fatigue research, including synchronous and asynchronous multiaxial loadings, was conducted by the team I work with in the previous research project. Fatigue tests were strain-controlled in elastic plastic strain range. Fatigue tests were conducted on 4 materials. However, in this presentation, the results for PA38-T6 aluminum alloy will be discussed only. My task was a microscopic analysis of small cracks on the surfaces of fatigued specimens, which were subjected to cyclic multiaxial elastic plastic straining. The results of this research will be published soon. They are an origin of current research. It is aimed to investigate the mechanism of initiation and propagation of small fatigue cracks in selected materials, subjected to multiaxial loadings, including asynchronous loadings. This surface topology is replicated using cellulose acetate thin foils. This technique is useful for observation of evolution of small cracks and the main crack formation. The picture on the left presents aluminum alloy specimens, and the picture on the right austenitic stainless steel specimens for selected loading cases. Thin-walled tubular specimens manufactured from PA38-T6 aluminum alloy were used. They were subjected to tension compression, torsion, and 90 degrees out-of-phase loading. The specimen's surface were carefully mirror polished using different grades of diamond paste in order to remove all machining marks and scratches. Fatigue tests were performed on Instron axial torsional servo-hydraulic testing system. Fatigue tests were conducted under normal and shear strain control using epsilon biaxial extensometer. The loading parameters, programs, and signal recording were conducted using Eastern Wavematrix software. The materials used for specimen surface replication are cellulose acetate thin foil and a set of auxiliary tools. The microphotographs were taken on a metallographic microscope equipped with 12 megapixel digital camera with dedicated image processing software. In order to capture features of the whole surface of specimen's working part, the first test was conducted in strain control mode. Next, based on the recorded displacement history, the second test was performed in displacement control mode. The tests were paused every 10% of expected fatigue life to make the replica on both sides of the specimen. The picture on the right shows a tool used to draw the reference mark system on replicas. The cellulose acetate sheet is attached by spraying a drop of acetone between tape and specimen. The acetone melts the tape, which sticks to the specimen. Next, it evaporates for 7 to 10 minutes. When the cellulose acetate is dry again, it is gently taken off with a plastic pencil and put between microscope slide glass. Very small details of specimen surface topography imprint on the replica. Moreover, the replica can be observed using transmitted light. Thanks to that, there is no interference caused by light reflection or curved surface effects. The greatest advantage of this technique is the ability to track the crack development history. To show the capabilities of this technique, the image of the replica and direct images of specimen surface are compared. All shots were captured in such a way that the vertical direction is in line with the specimen axis. The images present small cracks for the highest level of applied strain under axial loading. For this level of loading, small cracks could be observed from 60% of specimen fatigue life. The density of small cracks was much higher than for the low strain level, for which cracks could be barely seen after 90% of fatigue life. In both cases, the main crack formed in the very last cycles, that is less than 5% of fatigue life. They identified the image mechanism for axial loading in the applied loading level range was a coalescence of small cracks. The initiation and growth of small cracks followed a shared image mechanism. Cracks initiate and grow in direction of maximum shear strain, which are plus/minus 45 degrees for tension compression. Next, the cracks link with each other without a change in direction. The same damage mechanism was observed under torsional loading. Small cracks initiate and grow in the direction of maximum shear strain, that is perpendicularly and parallel to the specimen axis. Next, the coalescence was observed. In case of the out-of-phase loading, small cracks could be observed on many directions since principal axis, so also the shear strain vector rotates. The most developed cracks could be observed on the direction normal to the specimen axis. It corresponds to the plane of maximum shear and normal strain. On the loading level corresponding to similar fatigue life as the highest level of axial loading, coalescence of small cracks occurred. Differences in cracking behavior occur at the lowest level of out-of-phase loading. Much less density of small cracks was observed. All cracks propagate in the horizontal direction, but only after 50% of fatigue life approximately. The main crack formed in the last few cycles of loading from 4 cracks only, with an average length of 2 mm. These slides at the bottom right are the edge of the replica tape. Please note the coalescence of small cracks under axial loading. Cracks initiate and propagate on the whole surface in direction of maximum shear strain, up to 15 to 100 micrometers of length. After that, they coalesce to form the main crack. The small cracks occur at 0 to 45 degrees to the horizontal axis. In case of torsional loading, small cracks propagate on planes that are located at 0 and 90 degrees, which correspond to the plane of maximum shear strain. Small cracks grow longer, and, by contrast, they crossing most often. This was very rarely observed under axial loading. As it was already mentioned, for the highest level of out-of-phase loading, the small cracks initiate in many directions, forming a dense net. It can be clearly seen that the preferred direction of cracking is horizontal plane, on which maximum shear and normal strain act. For the low level of out-of-phase loading, that is, for the level on which small level of plastic strain occur, small cracks grow on the maximum shear and normal strain plane. From about 50% of fatigue life, the propagation of cracks could be observed. It can be noted that the density of small cracks is much lower compared to the other loading cases and levels. As a summary, I will mention the most important conclusions. Shear image mechanism was observed at the applied loading levels, regardless the loading case. The main crack is formed by the coalescence of small cracks. The exception was noted for the low level of out-of-phase loading, where the propagation of cracks occurred, and the main crack formed from 4 propagating cracks. The research is still in progress. It will be extended to some points to the lower loading levels to see if there is a change in the mesh mechanism. Other cases of loading than currently applied will be used, including asynchronous loadings. It is planned to perform the same research on austenitic stainless steel. Thank you for your attention.